Now we're going to look at practice problems. Yay! So in the practice problems, we start off with this plant. Okay, we can see that this plant is unstable. I obtain a state model for that plant. So in this case, I use the controllable canonical form. So the denominator is the coefficients. I'm sorry. The coefficients of the denominator appear in this last row. The coefficients of the numerator appear in the C matrix. In our problem, we're going to use a unit step that we're trying to track, and then this is our disturbance. Okay, so it's a DC offset sinusoid, and we can see that by comparison, this has magnitude 1, this has magnitude 5. So the disturbance is really large compared to the thing we're trying to track. Okay, so we're going to see how we can do again in this situation. We're pitted against a large adversary. Ooh, okay, how can we do? Is this going to work? Is our David going to slay this Goliath? All right, so we form W. So first of all, we notice here the pole here is at S equals 0. I do not have a transmission 0 at that frequency, so we're good. Notice we don't have to worry about the disturbance poles. So incidentally, this pole here is common to that pole there. So we don't have to worry about these poles in terms of the transmission 0. It's just this one that we're concerned about. So combining the two, we get this. So notice that the denominator here is the same denominator here. So basically what we're looking for here is the least common denominator between these two functions. So dv is in fact dw in this case. This is our controllable canonical form model for this transfer function. We get this model. Now I use the MATLAB code to compute the state feedback gain that I need. So here's my A, B, C matrices. Here's my AM and BM. I use these to get the proper dimensions. And then my A tilde is A and zeros of dimension n by m, where n is the length of the original A matrix, m is the size of this matrix, minus bm times c, am. Here's my B tilde matrix. I can now use Ackermann's formula, and in this case I place the eigenvalues minus 3, minus 4, minus 5, minus 6, and minus 7. So I use the Acker command to do that. And then I extract from KT, the K tilde, the KS and the KM that I'm going to use in the robust servo mechanism design. And in this case, I'm using state feedback for my controller. And so this gain here is actually KS. Okay. And so this signal here in designing this state space model, this signal here is actually X, it's not Y. So I multiply X times C, and that gives Y, and I use that for feedback here. So this is how I extract X from this block. And so here's my reference that I'm trying to track. Here's my disturbance that I'm trying to track, and this is a Simulink model for it. In terms of my state models, these are the actual matrices I put in there, A, B, C, A, B. So notice here, I, 0, and 0, 0 as our D. Okay, so those are the state models that I put, blocks that I put in there. So when we go through and simulate, this is the result we get. Boom. So what's going on here? Well, our system, this is the output of our system. Here's our reference that we're trying to track. We can see that at time 3, the response has locked on to the reference signal. Okay, so it works. It's tracking that signal, even though our system has this large disturbance that's entering. Okay, so notice that this signal down here is our control signal. And notice that our control signal basically sets up a sinusoid that actually cancels with the disturbance W, so that the net result, I see no evidence of W, that sinusoid, in the output. So I am getting, indeed, tracking and disturbance rejection. All right. So we're now going to try to apply this in observer feedback. And actually, we're going to use reduced order observer. So in this case, we're going to use a different, this is our reference signal. Notice I have a unit step that's delayed by 2. I have this ramp signal, and then I have this cosine. So when I take the Laplace transform of the signal, I get these 3 terms. Putting it all over a common denominator, I get this term, and this is my numerator. But I don't care what the numerator is. I'm mainly concerned about the denominator. It's a 4th order polynomial, and it has this controllable canonical form. Okay. Notice it's mostly zeros. These 2 zeros are because of the fact that I have these two poles at the origin. Okay, so there's my AM and BM controllable canonical form. So here's my plant that I'm working with, same plant as I had before. Oh, I'm sorry. So this is just an example of if I had this reference model, this is the controllable canonical form for that. All right. Well, I'm going to solve the same problem I had before with this unit step and this large disturbance signal. And now I'm going to do it using output feedback. And actually, I'm going to do it using reduced order observer. So up to this point, I have the exact same steps as I had before. Now, in my reduced order observer, I'm going to choose F to be this, okay, because my plant itself only has 2 poles. And so as a reduced order observer then, I'm already, in a sense, measuring one state. And so I only need to observe the other state. And so that's why F here is a 1-by-1 matrix. Okay, so in this case, it needs to be stable. That is, so I set it to be at -10. Okay, and then I use this function, reduced order observer, that takes A, B, C, F, and the state feedback gain, Ks, and returns L, Kz, Ky, and the transformation matrix T. So again, we use this Simulink model. Here's my system that I'm working with. Here's my observer. Here's my tracking model. And so this is the Simulink model I have. And so the only difference now is I have this observer. When I do the simulation, this is the result I get. It tracks the step, it rejects the sinusoid, and we can see the control signal provides a sinusoid that cancels the disturbance. Okay, cancels the disturbance. So that's the trick. That's the thing that we're working with. So we have an example. We see that the robust servo mechanism is a way of tracking a given reference. In this case, our reference is simple. It was a constant, and we can see it's tracking that, and it's able to reject a disturbance. In this case, is a sinusoid. I could have it the other way around. The thing that I'm trying to track could be a sinusoid, and the thing I'm trying to reject could be a constant. So you can do those different combinations of things. But either way, this approach will work as long as the conditions are satisfied. No transmission zero, stabilizability, detectability. Then we can get this to work. So this is the robust servo mechanism.